Okay, so this is going to be the final lecture on linear algebra. So before we move on to the next topic, so in this lecture we will look at you know this one advantage of diagonalization. So we talked about diagonalization of matrices, we talked about diagonalizability. So why bother with doing this, right? So among other things, it can help us work with functions of matrices. That's the subject of this lecture. And then we'll also look at a theorem, which is an important theorem, which is which can be profitably discussed in this context. Okay, so given an n by n matrix A, right? So oftentimes we are interested in looking at what A squared is. That's going to be another matrix. A cube is A power n, or in general some function of this matrix A. Now if it is a diagonalizable matrix, then this kind of a computation is greatly simplified. So all you have to do is work out the similarity transformation which diagonalizes it. If you are somehow able to work this out, D is equal to S inverse A is S. Then if you want to take the nth power of A, you just take the nth power of D, which is much easier to do because it's just taking the powers of the eigenvalues. D to the n is S inverse AS times S inverse AS all the way up to S inverse AS n times. Then you see that S and S inverse, they collapse with each other and you get identities everywhere. So then you have A times A all the way up to the nth A, and you have an S, so which is you can group together and you immediately see that this is the same as S inverse A to the ns, right? Now we can multiply left hand side and right hand side with S on the left side and S inverse on the right hand side. So and then we rearrange terms and you have A to the n is the same as S times D to the n S inverse. So if you can find the similarity transformation S, which can diagonalize your matrix, and of course the eigenvalues, then it's very easy to compute A to the n, right? And in general you can find some function of A using this the diagonal matrix and the similarity transformation, right? So this has great practical importance. So diagonalization of matrices is important, and there are for big matrices it's a whole industry to find to diagonalize matrices, and there are very, very sophisticated algorithms available for carrying this task out, right? But we are not going there. But I'm telling you that lots of physics problems involve diagonalization. Sometimes diagonalization of large matrices, and many calculations which involve matrices are best handled with the help of diagonalization routines, right? So this is just a very, very brief discussion of how diagonalization can help us to compute functions. So now let's look at a special kind of a function which is associated with any matrix, and that leads us to this theorem called the Cayley-Hamiltonian theorem, which is a non-trivial theorem which says basically that every matrix satisfies its own characteristic equation, right? So very simple to state and fairly easy to understand, but it's a non-trivial theorem. Of course, we are not going to prove it, right? So what is the characteristic equation? So it's just determinant of A minus lambda I is equal to 0, right? So the characteristic polynomial, you can also think of it as A minus lambda 1 times I into A minus lambda 2I all the way up to A minus lambda ni, if you know all the eigenvalues, right? So in fact you use this characteristic equation to compute the eigenvalues. You start with the determinant of A minus lambda I equals 0, then you work out lambdas, the roots of this polynomial equation, right? And then what Cayley-Hamiltonian theorem says is, in fact, the matrix itself satisfies the the characteristic equation. So once you have got all these lambdas, so notice that this is a statement about the eigenvalues, right? At this point we have not said anything about eigenvectors. So this is true for any n by n matrix. You find all the eigenvalues, you can put your n by n matrix into the characteristic equation, because it always exists for any n by n matrix, defective or not, doesn't matter, right? This is not about eigenvectors. And so this equation is satisfied by any matrix you correspond with, where the lambdas are the eigenvalues of this matrix. Now this is a polynomial equation of order n, so this means that you can expand it out, and it's like a to the n, some coefficient times a to the n plus some coefficient times a to the n minus 1 plus some coefficient times a to the n minus 2, so on, all the way up to down to I is equal to some coefficient times I is equal to 0. Now, which means that you will be able to write a to the n as a linear combination of the matrices I, a squared all the way up to a n minus 1. So in general, any higher power a to the n plus k can also be written as linear combinations of these matrices. So in fact, therefore you can write any function of your matrix f of a itself as linear combinations of just these n minus 1 matrices I, a squared all the way up to a to the n minus 1. So in fact, in principle, a function like e to the a can also be expressed as a linear combination of these matrices, right? So I have just stated this as a fact, and it's a useful fact sometimes, but from the point of view of completeness, we include just a short description of the Cayley-Hamiltonian theorem, right? With this, we come to an end of our discussion or of our foray into linear algebra. It's a vast subject, and if you want to carefully get into all the details, it's a like a full course in itself. But I hopefully we have covered all the salient aspects of the very beautiful and rich theory of linear algebra, and we will move on to the next topic starting from the next lecture. But some of the results drawn from linear algebra will be used later on also in other topics that we cover. Okay, that's all for this lecture. Thank you.